So this problem is about Kirchhoff's current law. And what Kirchhoff's current law is it just says that like at a junction, at a junction the currents add, right? So what comes in has to come out. So like I'm interested in this junction right here. So I have 4 coming in this way, so 4 comes in, and I have 2, so that's 4, and I have 2 coming in here, so 4 plus 2 has to equal whatever's going out here. So if I have 7 going this way, so 4 coming in, 2 coming in, that's 6. So that must mean I must have 1 coming this way, 1 amp. Right, so what comes in here is 4, what comes in here is 2, so that's a total of 6 coming in. If 7 goes out, then I must have 1 more coming in from the bottom. So that tells me that my current's going this way, and my current's going that way, and so so that's 1 amp going that way, so 1 amp. Right, so I've got 1 amp going in, so I'm going to go here. That was an easy one. Okay, next is about current density. So we talked about current density a little bit ago. So current density is J. So current density, J is current density. And remember, current density, the units are current per meter squared. So remember, it's current going through the air, like the end of a hose, you know, the circle, the face of the hose is, the area is pi r squared. So current divided by meter squared, or amps, A divided by meter squared. And usually that, I guess I should write, this is area, sorry. Area, right? And if I have a hose, if I think about a hose, right, so this is going to be the area right there, and so that's pi r squared, right? So so just looking at this, my current density, I've got amps per meter squared, that matches here. I see a pi over here to make the math easier, right? That comes because my area has a pi in it. And I'll just be able to say J is equal to that number when I plug in. And so it's asking me, what is the measured current through the wire? So I've got my formula. So over here, I know J is equal to current over area. So I can solve for current. So I is equal to J times A. Okay, so I have a diameter of my copper wire is 4 millimeters. And so that's 4 times 10 to the negative 3. So I can just plug in. So I is equal to, let's see, 5 times 10 to the 3 divided by pi. Right, that's my J, amps per meter squared. So that's, I plug that in for J, times for area, pi, and r squared. So that's going to be my 4 millimeters, so 4, I'm going to put it in terms of meters, so I'm going to say 4 times 10 to the minus 3, millimeters is minus 3 meters, divided by 2, because that's the diameter, so I need to get the radius squared. So I'm going to say this is equal to amps, because these areas aren't the same thing. That A is the same thing. That's amps for current, and then this A is area. So pi r squared is my area here. Right, and if I multiply through, I'm going to get I is equal to, let's see, so this is 2, so let's see, I is equal to 5 times 10 to the third. I'm going to leave the units out for now. I've got amps over meters squared, and I'm going to have meters squared on the top here, so I'm just going to get amps for units. But it's always nice to check. I get to cancel my pi's here. That's handy dandy. And now 4 over 2 is 2. So that's going to be, this really is 2 times 10 to the minus 3 cubed, right? So I'm going to have 2 times 10 to the minus 3 squared, sorry. And so this is just 2 times 10 to the 3 times 2 times 10 to the minus 3. So that's 4 times 10 to the minus 6. So that becomes 4 times 10 to the minus 6. So if I do 20, or why do I have a 3 here? That's weird. I need to, sorry about that. This is not right, as you probably know. So I have 5 times 10 to the third times 4 times 10 to the minus 6. So that's going to give me 20 times 10 to the minus 3. And so that, and that's going to be amps, and so it's going to be 20 milliamps. So it's going to be C. Great. So now, for 6, this is for the wire in the previous problem. Okay, great. What is the electron drift speed? So wire in the previous problem, remember that we know what our diameter is. So our diameter here is going to be 4 millimeters. What else do we need to know? Let's see, actually I wrote this one down somewhere. Yeah. And I think we need to know its current. Yeah, that's right. We need to know the current. So we know our current is I is equal to 20 milliamps. And so this problem is asking about electron drift speed. And so I remember always being confused about electron drift speed, but all it really is the speed of an electron. So if I have a wire, right, and this wire has a whole bunch of electrons in it, and when I attach this wire to a voltage, to a battery or something like that, what's going to happen is the positive side of the battery is connected on this side, the negative side is over here. I'm creating a potential difference, and that's going to cause all my electrons in that wire to move, right? To either move to the right or move to the left. And so they're all going to have a speed. So that's what I'm looking for, is I'm looking for its speed. So I'm really, when this is electron drift speed, what this really means is V for velocity, right? And I don't care what direction it is. So speed, I'm not going to give it a direction. One of the things it's telling me is N is the electrons per meter cubed. So that's going to be E over meters cubed. And so that's a volume, right? Great. So there's a really good site online that shows you a good picture of this, which I think is really helpful. And I actually was sending it to you. So let's see if I have that link. Yeah. Go to the link. So this is a really good description. So N is the same N in your problem. The number of charges, E, so the charge on electron E per unit volume, right? So N's of an electron density, the number of electrons per volume. Charge, right, is the number of electrons, so my charge density times my charge, right? So that just gives me my number density, times area times distance. And so really my area is, so remember N has a per volume, and I need to get rid of the volume in order to know what the speed is going to be. So this is going to be my area, right? And so you can see that right here. The area is here, or the area is there, and my time is the distance that the electron goes divided by the velocity, or velocity is equal to distance times time. So I can find my equation by saying, well, current is equal to the charge divided by the time, right? The charge divided by time, and I can get charge from this equation. So it's the number of charges per unit volume times the charge, right? So when I just have the number, it's just how many, but I don't have charge yet, right? I need to say how many electrons do I have? This tells me how many I have in a volume. I can then multiply them by the charge for each one. That gives me charges per volume. And then I can divide by the volume to have charges, to just have charges. So that gives me the Q. So if I go back, then let's go back to my little handy dandy recorder here. So this is V is going to equal to the current, right, divided by, or sorry, let's start with, so current, oops, didn't want to do that either. Current is equal to the number density, N, times the charge, E. So that number of electrons times the charge. So now I have charges per volume, because this is a number per volume. Number of charges times the charge on an electron, and then volume is in here, number of volume. And then A for the area times V, the velocity. So if I think about units, right, I'm going to have current. So current is in amps, or charges per time. This is going to be the number of electrons times the charge on an electron. So that's my charge. So charge per time, Q over T. I'm going to have the number of charges, number of electrons times the charge on an electron. That gives me my Q, right? This is a volume. So I'm multiplying. This is electrons per meters cubed. So electrons per volume. So I'm going to get rid of an area, right? And then I'm going to have velocity, which is a distance per time. So the distance cancels with that extra meter here for this density, and then divided by time gives me my time here. So then I can solve for V is equal to I over N E A. And if I plug in, I'm going to have 20 times 10 to the minus 3 volts, or amps, to make that an A, divided by, see if I can erase that, and then 8.5 times 10 to the 28 electrons per meter cubed times an electron, which is 1.6 times 10 to the minus 19. And now times, on the bottom, right, times area, which is going to be pi, and then r squared. So I'm going to have 4 times 10 to the minus 3 meters, and that's my diameter, and I need my, divided by 2, I need my radius squared. And if I multiply all that out, I get V is equal to, if I can find my slip of paper again. Of course I can't. Yeah, I end up plugging all that into the calculator, and I get like 0.36, so round it up to 0.4 times 10 to the minus 6 over pi, and you get meters per second, which is a velocity. So all that's to say is I remember as a student, like really trying to go through and understand what this number density was and what electron drift speed was, and it's really just a speed. So it's just a speed that an electron travels when you hook it up to a potential difference. And you have to realize that the whole volume is filled with electrons, and so you really need to get rid of the area to think about just the distance along the length that it's traveling.